Hi everyone, and welcome to another session of Dev Days Europe 2022. We have prepared lots of interesting talks, so I kindly urge you to stay tuned and enjoy yourself. At the end of the session, you'll have time for Q&A. You'll have time for Q&A, and I kindly urge you to use the Q&A section to post your questions, and our speaker will be answering them. Keep in mind also that our Knowledge Partner Pact will be giving away 20 ebooks to the most active conference attendees. So I kindly urge you to participate and be active, rate sessions, leave comments, ask questions, and you can win a great ebook from our Partner Pact. Okay, let me introduce our speaker, Huseyin Babal. He's a senior software engineer, and at the moment he's building software as a service applications for challenging technologies with a multi-cloud environment by using Kubernetes at core architecture. Huseyin has also architected microservice and DevOps, transitioning for big scale projects. He uses Java, Spring Boot, Golang, Kubernetes for software as a service applications. The topic that Huseyin will talk about is the practical Raft consensus, and in that session, Huseyin will talk about how Raft consensus works in theory by supporting live diagrams. During this talk, he will also provide real-life use cases about Raft consensus, and that's it. You can feel free to enjoy the session. Huseyin, how are you?
Fine, thanks. And I am about to share my screen. I will content. I assume you see my screen, right?
Yes.
Okay. Um, uh, Thanks, Emil, again. Hi, everyone. My name is Huseyin, and in this session, we will try to get into theory of Raft consensus, and then I will try to show you a couple of examples about how it works. But let's start with the explanation first. Raft is stated for replicated and fault tolerant, and you will see it is designed for making distributed consensus very simple. So there is already a technology which is called Paxos for more than 25 years ago, and most of the time the consumers were complaining about the complexity of the design. So let's have a look how Raft solved this problem in an easy way. When you have a look at the Raft consensus, there, of course, in real life examples, when you say Raft consensus, it mostly involved in the clusters. And this kind of clusters, they contains nodes. You can say that they are servers. In a typical scenario, a client connects to a cluster, and what client sees a single state machine. But at the end, there are multiple servers here, the actors, and they all have their own state machines. And these state machines can be transitioned from one state to another. And these state machines are mostly integrated with the log messages that we can see in the upcoming slides. So there is only one state machine. Think about that. It can transition from A to B to C to D, and it can even go to C to C in this diagram. But in a distributed system, since there are multiple servers, then once a client try to do something, there can be multiple state machines here, and they are called replicated state machine. When a client try to contact, or let's say that they are trying to put some data into this cluster, and there is a consensus module in this typical. So when you have a look at the implementation of Raft consensus, you will see there is a consensus module. The first thing it does is, this is a command. When you put some data, it is a data put command, something like that. And we can think that this is a binary data. And you do some changes on your state machine, but at the end, these requests are always forward to leader. So if you want to do something, that node should be a leader. And once leader get this request, they send this one to another server, and this server also put this data into its own log entries, and then it sends this request to another service, and this service put this data into in all own log entries. Then at the end, this leader just updates its status saying that, okay, I finalized everything. I have synchronized, replicated this data to other members, and then now I am safe. I committed this data, and here your response. This is something like transactional operation. So you, within a transactional scope, you do multiple things. Multiple things refer to putting some data into different servers and then marking your transaction as succeeded. So how it is simple then? When you check the Raft consensus algorithm, you will see there is a leader election. This leader is so important because whatever you do, they are all handled through the leader members. Here, leader, there can be only one leader at a time in the system, and whenever it crashes, there should be a new leader selected in a short time of period. And this is the leader election part, and it is mostly connecting between interaction between the servers. And the other part is log replication, so the main data. So the log replication contains the main data, and leader gets this command and append this data to its own log. So think about something like database. It is a folder inside the operating system, and it is called its log, and there is log entries inside this log system. um, uh, of course, there is a third part, which is safety. In a distributed system, it is not so that easy to maintain the members all the time, and they should be always up to date between each other. So here, when you write a data in order to write the data in the leader permanently, you need to be sure that this data is replicated to other members in a correct way. So here, when you have a look at the specific node, I am not talking about the entire distributed system, but just we are checking a node. It starts as a follower. So you are follower in the beginning. If there is no heartbeat, and in this follower mode, it is passive. So you only expect to see some kind of heartbeats. There is a leader in the system, and it is always broadcasting these heartbeat messages to the followers. I am a follower. So let's say that there is a defined timeout value for this. If I cannot get this heartbeat message until within this specific time period, then I will try to become a candidate to become a leader at the end. Here I become a candidate, and when I do that, if there is a higher term, so I will talk about term, but if I became a candidate, then I request vote from the other members. And if I get enough vote from the other members, then I can become a leader. And after that time, I will be leader, and I will be accepting the request from the client side, and I will append this data to my replicated log. And you need to send heartbeat messages all the time after this point once you become a leader. Here in the Raft consensus, you never talk about time, because time is something can be flaky. Because think about this, you are doing a mission critical operation, and you have multiple servers. If there is an inconsistency between in terms of this date time between these servers, then you will be in a trouble. So instead of using time, Raft consensus uses something else, which is called term. So it is started from a 1, and then whenever you do a new election, this will be incremented by 1. So let's say that you have started your cluster, all the members are up and running, then the term will be 1, and there will be election. So think about this blue boxes here. That is the time which is used for elections. And then you replicate data. Okay, it can be one or multiple times. If there is a problem, you see there will be another election here, and there can be another one. You see the elections may take more time than expected, time to time. Here you have a more longer healthy cluster time, but here you see a leader is elected, but after a short time of period, it is crashed again, or that something happened differently. You see here there is only one blue box. That means they try to do an election, but it is timed out. And they just try to do another election, and in turn 5, it is succeeded, and leader selected, and so on. Here again, the most important part is there can be only one leader at term in one term. So in term 3, you can see only one leader. There cannot be multiple leaders here. And as you can see here, there is no leader because it is failed. And here we are talking about servers, but the server information is not maintained by Raft consensus itself. So when you start your members nodes, you need to maintain these IP addresses or host names, or if you are using Kubernetes, you need to maintain these endpoint addresses on your own. When you try to request vote from other members, if your information is outdated, then you will fail again. You will become a follower from the candidate. So in the leader election, you become a candidate, increment the term by 1, and you first vote for yourself, right? And if there's a timeout, you can increment that by 1 again. So whenever you get a timeout, you increment it by 1. And when you say request vote, you need to get the vote from majority. So what is this majority means? So let's say that you have 5 members in your system. You can add 1 to 5, which means 6. You can divide it by 2, and which ends up with 3. So if you get 3 votes from the members, from the followers, you can say that, okay, I am the leader. But think about this. There can be multiple candidates. They are doing some kind of election at a time in term X, let's say that. They can get votes from the followers, but at that time, they need to check whoever gets more votes from the followers, then they will become a leader on this time. Um, Here, as I said, one of them got 2 and another got 3 votes, then S2 should be a leader in this case. Each server, each member, each node, whatever you say, then they should vote on for once per term. So you cannot give 2 votes within a specific term. Better to have random timeout values. Think about this. You have a system, you have 5 members, and then all the members have a same timeout value. That means whenever there is a problem with the leader, you will see they will try to start the election at the same time if you have same timeout value. But if you make it randomized, let's say that between 150 and 300 milliseconds, then you will see all members will have different timeout values, and most of the time, uh, only one of them will trigger this election because it will be timed out first before them. And here you need to carefully design this timeout value, because here, whenever leader or append entries, you are sending this data, right? This is called broadcast. And this broadcast, average broadcast value, timing value, should be less than this timeout value, right? Because think about this, if broadcast is 1 second, and if your timeout value is, let's say that 500 milliseconds, and you will try to trigger this election all the time. So you need to be careful about that. In a typical scenario, let's say that happy path, client sends a command to leader, and leader appends this command to its log, but it is not committed yet. Leader sends append entries. So this append entries is a general term. Even in the white paper, you can see these append entries. And the calls are called RPC. You can see HTTP, you can see gRPC implementation, but at the end, they are called RPC. They send append entries request to the followers, and they get majority, and then leader notifies follower for the committed entries again. But here, there should be a consistency, right? You are managing a distributed system data, so you should be responsible for consistency of this data. When you say append entries, it always contains index and term. Term, it is referred to timing, but let's say that the election, it refers to election. And then index. Index means you are putting data into your own log entries, log system. So you have an index there. And whenever you try to send, okay, I want to become a leader, then your index will be compared. You send a request to follower saying that, okay, I want to be a leader. They check your index and term. If it is outdated, they fail your RPC request. And also, a follower rejects request if there is no matching entry. Here, um, let's say that one of the nodes is crashed. It is follower. They restart it again, or you just added another member into the cluster. Let's say the scale up operation. In this case, leader is responsible for sending the log request to the this member, right? If it is a crash operation, most probably when they recovered, they have some data inside it. They can be outdated, they can be corrupted in a way. So what leader does on this case is it try to send the latest log and to this follower. If there is a mismatch, then it just decrease the index by one and try to send again. If it is not matching, then decrease and decrease up until it goes to the first entry. For a new member, you can think that the leader will try to send all the data to the new member. But for the existing member, and if they crashed, the ones they crashed, then it will try to find a possible index here. So let's see a couple of diagrams. This happy path leader has its own log entries, and there is follower at a time t. When there is a new message is committed into leader, the leader will try to send this one to follower, and at the time two, you will see this new member, new term, and new a command. Let's say that it will be appended to the follower. And here, what you see, this is the term 1, 1, 2, 3. And let's see about mismatch. In leader, let's say that we had two items here, logs, and there are two more. And as you can see in the follower at the time t, they are mismatched. So three mismatch, two mismatch. But that is there is a match here. In this case, what the leader will do is they will try to retry again and again by decreasing the index here. So it tried to send three, doesn't match. Again, doesn't match. But here it matches. So at the end, you see one, this 3 and 6 is here, but 2 and 3 is sent by the leader. As you can see, if there is an inconsistent data, it will be overwritten by the leader. Leader always has the up-to-date data, and they are always true. And you need to expect some data overwritten operation as a follower. Um, Okay, we just explained this one. So after this point, I will try to show you a couple of code examples by using Golang, of course. This code is compilable, but actually there is no entire business logic inside it. There will be a pseudocode, let's say that. Just to rephrase this big picture, you start as a follower. Um, if there is a leader failure, you try to become a candidate, but you are saying, oh, there is a new term, then you go back to the follower state. If there is an election timeout, again, you will be retry as a candidate. But if you get majority of the votes, then you will become a leader. Let's have a look at in the code base what we can do about this. As you can see, we have eight steps here. There will be an initialization. Let's say that you added a new member into the cluster. There will be an initialization at this stage. Voting for a new leader here. If there is a RPC request coming to you, then you can respond to this leader by checking the logs, terms, whatever healthy. Collecting votes, which means when you become a candidate, you collect logs. You can broadcast messages. You can do a leader to follower replication. You can be sure about that. Receiving messages, updating follower logs. Leader log acknowledgement means you are saying that, okay, I sent the I replicate the log to follower, and then I get the result. And then leader committee logs messages. So as you can see here, there is no separation. So we cannot say that, okay, leader to follower replication can exist only in the leader machines. There is no such a stuff. So all the business logic exists in all the nodes, because time to time a follower can be a leader. So this exact code base should be inside all the cluster members. But this logic is handled by some kind of if statements. We will have a look at that one. What you will see here, the entire code base, let's say that there is a package which is called Raft, and this refers a node. Let's say that there is a node interface, and we will check the capabilities of this node interface. And this is the methods we already defined in the previous slide. Let's have a look at the data structure first. We are saying that we can send log request, right? We are saying that, okay, could you please put this log into your system? Here, this log request is used inside the append entries. You are saying that, okay, follower, could you please append this into your log? Here is the log. By doing this, you provide leader ID, you provide current term, log length, prevlog length, commit length, and entries. Here in entries, there can be one message, or there can be multiple messages, or whenever it is an empty. So normally, if there is no message, you can think that, okay, you don't need to send these logs to the followers. That's not true, because append entries is used for both uh, putting data into the followers plus sending heartbeat messages. If you send append entries with empty log request, you will see it will act like a heartbeat message, heartbeat check. Okay, I am leader, I am here, I am healthy, you are saying this one. When you say that, you will get a response from the node. It will say, okay, here is my node ID, here is my current term, and okay, I acknowledge this operation, and if there is some kind of failure, you can also put this here. When you have a look at data structure of log itself, it contains commands or binary data, whatever you have there. Um, it contains message, binary data. That's why I put interface. You can also use byte there, byte array, and term. Of course, it is important because um, the data is validated on the each side by using this term value. Vote request, here you are saying that, okay, this is my node ID, this is my current time, log length, and last term. Okay, I just want to do this vote operation, and of course you get vote response. It is same with log request and log response. Okay, so we check data structure until this point and whatever the capabilities in this node interface. And then, of course, this node will keep some kind of state. In Raft consensus, the logs are persisted into. Okay, let's rephrase it. Raft consensus is not responsible for the way of how the data is handled inside the system. It says that, okay, here is the function that you can use, and just put your business logic inside that. You can simply write into the file system, you can write to another place, it is up to you. But let's say that there is a technology which is called, for example, BoltDB. You can use BoltDB to maintain your data. Here we are keeping state. These logs are persistent into the disk, but the remaining data are all handled inside in memory, right? For example, when you initialize your cluster for the first time, I mean the member, you will see everything will be started from scratch. But after you do some kind of operation, these values will be updated, and that is a clearly a state for this specific node. Um, Here, for example, there is voted for. It is for preventing putting multiple votes per for the term, right? Here, the string is term, and then this value is something like true. That means, okay, before sending this vote for, before sending an actual vote, you can check this vote for map to prevent multiple vote operation. Whenever you write data into log entry, this commit length also updated. Current role, you are follower, candidate, leader, whatever it is. current leader, you need to be sure about current leader all the time. Why I am saying this one? Because it can have multiple reasons. For example, when you get a request, vote request from the leader, you can send it back to the other side. Also, let's say that you got a request from client. It can be, by the way, let's say that client maintains the server member list on its own, and I have leader address. Let's say that some IP address, and let's say that there is a problem in the cluster. Leader is changed, but on your side, you just have outdated leader address. You can still send to this address, but once that follower or candidate, whatever it is, when they get this request, they can be able to forward this request to leader. So this is how current leader information is important for this scenario. Votes received also is important. It contains the node IDs so that you can count this vote received and then decide to become a leader. Here, let's say that in order to request some vote, you sent 5 votes, you got 4 acknowledgements. So you keep this data count inside here, send length and act length. Node ID is your current node ID. Again, this is your auto-generated node ID. It can be UUID, it can be some incremental number, but you need to maintain that one. Typically, let's say that you are inside a Golang code base. When you say new node, it will create a new, let's say that member actor inside this Raft consensus. In the beginning, you will see the current role will be follower and your node ID will be node ID. So that means in the new node, you need to pass node ID. So it is maintained by you. And there is there's something there. You see Go and that send periodic heartbeat. So maybe you are not familiar with Go, but this is something like a concurrent operation. You're, let's say, creating a separate thread. Here we are using Go routines. This periodic heartbeat, this is called, but it does not necessarily to be executed all the time. It is executed only if you are a leader, right? Because leaders send periodic heartbeat. And you are saying that, okay, here is my node. So you simply return node information from this operation. Okay. This is not a new node, but let's say that there is a problem and you started your node again, not from scratch. And here you define some the initial values, current term, what for. You see they are all empty or default values, but in a short period of time, they will be all updated. Leader will overwrite all of your data soon. Um, if there is a crash, then there can be a recover. So you may ask that, okay, Hussein, why there is init and recover differently? That's because you can implement a different mechanism for recover operation. So when you say recover, maybe you can simply get some data from disk and then use it as your state. It can be such a case. Recover is for that operation. Or you are starting your cluster from the beginning, then this recover may be a good part for you. And trigger election. We said that there can be multiple reasons for trigger operation. So why it is triggered? That is because there can be a problem with the leader. It can be crashed, or current election is timeout. So there is an already election, but it is timed out. So in trigger election, you can see again this node list. We need to have this nodes list because in order to get votes, you need to send RPC requests to these nodes, right, to get vote response. First of all, you increment your term by 1 because this is the number one rule for the election. You increment the term by 1 and then continue the remaining operations. You are typically a candidate and then you vote for yourself. You see, voted for, not ID, is true. So this is yourself. And vote received, again, the received list contains as a first member the current node. And if last term, initially last term is a 0, but if there is some entry in the log, then last term is updated by this term information in the log. So you get it from the log itself. and you send a vote request. Okay, everybody, could you please get this message? Vote request is, you see node ID. This is your current node ID, current term, log length, and last term. Here in a for loop, you are sending this vote request to the entire members, the other members, and it is maintained by you. After this operation, you start a timer. There is a method, but I don't. We don't need to necessarily see the code base of start timer. But let's say that there is another thread, another go-to routine, whatever you understand well. It just tracks this election time, and it times out after a while. So if there is a timeout, then this election will be automatically failed. And vote. So here, let's say that leader sent a vote request, and as a follower, you got this request. Here, you are checking basically two things. First of all, you get as a follower, you just grab your current term from your log entries, and then you check two things for this request. Is log okay? Is term okay? So in order to check log, you see you are checking last term, and it should be greater than current term, right? Because if last term is less than current term, if the leader term is less than follower term, then there's a problem. Leader is not a real leader, something like that. And is term okay? Again, we are comparing the terms. If both log and term is okay, we are saying that, okay, as a follower, here is my current term, here is my role. I voted for this node ID. So you see request node ID. This is leader. So in the follower, I am saying that I already vote for this leader and send vote response. I am simply returning an RPC call and I am providing my information there. If log and term is not okay, then I am failing the, so you see result, I am failing this response so that the leader will not count my vote request as a succeeded one. And receive vote here. If my current role is candidate, and he again, receive vote can exist in all the members, but not all the members are candidates, right? If your current role is candidate, then you can think that, okay, this code piece is designed for me. Then here what I am saying is, you remember this calculation. If you have, for example, 9 nodes, you add by 1, which is 10, divided by 2, then it is counted as 5. So if I get 5 received node votes from the followers, then I can say that, okay, I am the leader after this time. My current leader is node ID, my node ID, and cancel the timer. You don't need to track the timer anymore because the leader is selection is succeeded. And here, what I do is I am iterating all the nodes, and I am saying that, okay, I have all the up-to-date data. Here is my logs. Just override your data with this. Okay, and here, if it is not succeeded, then we are saying, okay, I am going back to the follower state and then canceling the timer on this case. Maybe this timer can be located here after the if else, but yeah, that's just a pseudocode. Broadcast. This operation is very, you can think that this is the part mostly you handle on your own, because broadcast means you can replicate log data to the followers, and if you have lots of data for the newcomers, it can be a bit pain, right? So you need to implement this one very carefully. You can send data or you can send heartbeat messages by broadcasting. Again, nodes are maintained by you. Here, if your current role is leader, then you are saying, okay, here is my, I am adding these log entries to the system. It can be one message, so broadcast message. There is only one message. I have my own log entry, and then I am adding new log here, and I am sending these entries to the entire members by using this for log, replicate log. And if I am not a leader, you see, forward. This is critical because since it is expected to see leader always changing in the Raft consensus environment, then you cannot force your clients to track this leader information all the time. So okay, as a client, you send a request. It was a leader before, but now it is became follower. When you send your request to this follower as a okay, put my data into log entry, then it will forward your request to the leader, and it will be beneficial to return to the client as okay, it is something like a modified response, and you can return the actual leader's information to not send this information to leader again and again and again from the client side. This periodic heartbeat, as I said, it is a replicate log. So again, you need to know nodes. If your current lead role is leader, you are iterating all the nodes, and if this, of course, this nodes also contains your own information, you should skip that part, and for the remaining one you need to send this log message to the followers. As you can see, there is no log information here because it is a heartbeat message. Replicate log. So here you are a leader and there should be a follower. This is for sending a replicating log to only one member, one follower, not the entire followers. And here we are saying that if there is a new message, then our prev log term is calculated from the existing log, and we are saying that okay, could you please replicate this log information. So what is the content of this? Here is my leader ID. This is my lead. I am leader. Current term, log length, again prev log term, commit length, and entry. So this commit length is important because, as I said before, this is the result of a transaction operation, right? When your transaction is succeeded, you that means you also committed in your leader log entries. And entries to be sent here, list of the logs. That's it. Why there is a array slice operation here? This is simply array slice because first of all, you send your request to the follower. If there is a mismatch, you decrement it by one, send again. If there's a failure, decrement again and send. This is how it maintains the consistency. For handle log request coming from leader. So you are a follower, and you are checking if the log is okay. Here, if the log is okay and current term is matching, then you directly saying that okay, I am follower, here is the leader, and I am appending these entries to my log. This is the happy path. The terms are matching. But if there is another case, then you need to say that it is false. Then this replicate log operation can get this failure, decrement the index by ID, and resend these log entries to the follower again. Handle log response, it is something like okay, you are a leader, right? You got a log response, you send okay, just append these logs, you get a response. If you are a leader, then you check the result. If result is okay, you say that okay, commit log entries. If there is a problem there, this is the thing, we just decrement our index by one and then replicate the log again. If response current term greater than the my term, then I am not a leader again, right? I am trying to send some data, but my data is already outdated. Then follower says me that okay, you are not a leader, you cannot be a leader because I have up to date data than you. Then I automatically become a follower in this case.
Hussein, sorry to interrupt. We
Yep.
have 5 minutes left, and
Mhm.
I kindly urge the attendees to ask their questions in the Q&A section. Thank you.
Yep. Yep. Okay. And in the commit log entries, since you get minimum acknowledge from the system, then you can. So you see here in this if statement, this is the business logic you can implement on your own. What does commit log entries mean? You have a disk, you are using BoltDB to maintain this log data, and that's it. So it is up to you. In order to test something, you can even print some data here, system out or something like that. And append entries mean this is also again this adding this data into the system. And when you have a look at parameters, there is log length, leader commit length, and entries log. So here your log length, leaders commit length, and entries, you are simply adding this data to an array here. N.log refers to your log entries. It can be in memory, it can be on disk, whatever you prefer. You are simply appending this data to here, actually. And that's it on my end. If you have any kind of question, yeah, I can answer them in Q&A. Um, um, Thank you for all of you for listening this session.
Yeah, we'll be waiting for questions now. Don't be shy. Ask whatever you want. Thank you for the great presentations, Hussein. It was very interesting,
You're
very
welcome.
informing. We don't have questions. So I guess we can wrap it up. Thank you very much, everyone, for your attention, and see you in the next sessions in the conference Dev Days 2022. Thank you, Hussein, for your attendance. We'll be happy to have you again here.
Okay. Thank you all. Have a nice
Thank
day.
you. Bye bye.